Plasma anion gap is a measurement of the balance between positively charged ions, called cations, and negatively charged ions, called anions, within the plasma. Its normal range is typically between 3 and 11 milliequivalents per liter. While anything below 3 milliequivalents per liter is considered abnormally low, and above 11 milliequivalents per liter is usually considered abnormally high. Now, at every moment, there are trillions of cations and anions floating around inside our blood vessels. For them to happily and stably coexist, the plasma has to be kept electrically neutral. That means that the sum of all positive charge from cations has to equal the sum of all negative charge from anions. The vast majority of cations are sodium ions, or Na+, followed by potassium ions, or K+, then calcium ions, or Ca2+, then magnesium ions, or Mg2+, and finally various positively charged proteins. The majority of anions are chloride ions, or Cl-, followed by bicarbonate ions, or HCO3-, then phosphate ions, or PO43-, then sulfate ions, or SO42-, and finally some organic acids and negatively charged plasma proteins, like albumin. So let's say that we try to measure the concentration of cations and anions in our plasma. Unfortunately, not all the ions are easy or convenient to measure. Specifically, among cations, usually just sodium is measured, which is typically around 137 milliequivalents per liter. And among anions, chloride is measured, which is about 104 milliequivalents per liter, as well as bicarbonate, which is around 24 milliequivalents per liter. So just counting up these three ions, there's a difference, or gap, between the sodium concentration and the sum of the bicarbonate and the chloride concentrations in the plasma, which is 137 minus the sum of 104 plus 24, which is equal to 9 milliequivalents per liter. And this is known as the anion gap, or in other words, how many more cations there are than anions. Now, just a few seconds ago, we said that the positive charges must equal the negative charges. So why does this gap even exist? Well, it's because sodium accounts for the vast majority of cations in the plasma. But by measuring only chloride and bicarbonate, we're ignoring a bunch of anions, including the anion component of several organic acids and negatively charged plasma proteins, like albumin. In other words, this anion gap represents all these unmeasured, ignored negative charges out there, and normally ranges between 3 and 11 milliequivalents per liter. If the anion gap is high, it's usually because there's a high amount of these unmeasured anions. Calculating the anion gap is a useful diagnostic tool, because it can help identify potential causes of metabolic acidosis. Acidosis refers to a process that lowers blood pH to less than 7.35, and metabolic refers to the fact that it's caused by a decrease in the concentration of bicarbonate ions. One way that the bicarbonate ion concentration decreases is by binding to protons, or H+, which results in the formation of H2CO3, or carbonic acid, which subsequently breaks down into carbon dioxide and water. These protons come off of various organic acids. For example, in the case of heart failure, when not enough blood is pumped to the tissues, the cells won't have much oxygen. When not enough blood and therefore oxygen is pumped to the tissues, the cells can't break down glucose, so they're forced to accumulate lactic acid molecules, each of which has a proton that it can donate, and that's known as lactic acidosis. Another situation might be diabetic ketoacidosis, which leads to a buildup of keto acids, which are also molecules that carry along a proton. Yet another situation might be after accidental ingestion of ethylene glycol, which is a common antifreeze. This can cause oxalic acid to build up. Also, a metabolite of methanol, which is a highly toxic alcohol, is formic acid. Paint or glue has a molecule called toluene, which leads to a buildup of hippuric acid. One more cause could be from chronic renal failure, where uric acid or sulfur-containing amino acids build up because the kidneys simply can't get rid of them. Alright, so to help better explain this, let's say that you have one of these organic acids, and then a sodium ion and a bicarbonate ion. so one positive and one negative ion, meaning that we have electroneutrality. At a physiologic pH, these organic acids dissociate into protons and corresponding organic acid anions. That proton quickly grabs its bicarbonate ion that's floating around, forming a neutral molecule. So, since we still have one positive ion and one negative ion, we still have electroneutrality, since we lost a bicarbonate ion but gained an organic acid anion. Now, we still lost a bicarbonate ion though, and this decreases bicarbonate's plasma concentration and shifts the pH towards the acidic range. If we remember our anion gap equation, we have sodium, which is the measured cation, minus chloride and bicarbonate, the measured anions. So on the left you have 1 minus the sum of 0 plus 1, which is 1 minus 1 or 0. On the right side we have 1 minus the sum of 0 plus 0, since the organic acid is unmeasured. And so this equals 1 minus 0 or 1. So we see that even though we're still electrically neutral, our anion gap increases, and will be high in the cases of increased organic acids. But that's not what happens in all cases of metabolic acidosis. For example, with diarrhea, excessive bicarbonate gets lost in the stool. And in renal tubular acidosis, excessive bicarbonate gets lost in the urine. In these cases, the kidneys start reabsorbing more chloride ions, which build up in the plasma and replace the bicarbonate ions. Since chloride ions are measured in the equation, the bicarbonate concentration goes down, but the chloride concentration goes up. So the anion gap stays about normal. That's why a normal anion gap metabolic acidosis is sometimes called a hyperchloremic metabolic acidosis. A lot less commonly, a high anion gap might be unrelated to a metabolic acidosis, and instead might reflect a buildup of some of the unmeasured anions. Some examples are hyperphosphatemia, or increased plasma concentration of phosphate, hyperalbuminemia, or increased plasma concentration of albumin, or IgA producing multiple myeloma, where IgA immunoglobulin, which is an anionic protein, is produced. To keep the total charge in balance, when there are more unmeasured anions around, the bicarbonate and chloride concentrations decrease. As a result, the anion gap goes up. Now, a small elevation in anion gap can be seen in metabolic alkalosis. This is because a high or alkaline pH triggers albumin to release protons. This results in an increase in the net negative charge on each albumin molecule. Once again, there are more unmeasured anions around, in the form of albumin, and the bicarbonate and chloride ion concentrations go down, which makes the anion gap increase. In rare cases, the plasma anion gap can be lower than normal as well, which is typically defined by less than 3 milliequivalents per liter. This can be caused by a decrease in the concentration of unmeasured anions, for example due to hypoalbuminemia, or decreased plasma concentration of albumin. To prevent the overall negative charge of the plasma from decreasing, the bicarbonate and chloride concentrations will rise, which means that the anion gap will fall. Even more rarely, a low anion gap can result from an increase in unmeasured cations, like in hyperkalemia, or increased concentration of potassium, hypercalcemia, or increased concentration of calcium, hypermagnesemia, or increased concentration of magnesium, or in individuals with IgG producing multiple myeloma, producing IgG immunoglobulins. Interestingly, IgG is cationic, whereas IgA is anionic. Just like before, positive and negative charges in the plasma need to be maintained. So essentially, sodium concentrations will fall off and the anion gap will get a lower value. Alright, as a quick recap, the plasma anion gap is the difference between the plasma concentration of sodium and the sum of the plasma concentrations of chloride and bicarbonate, and represents the unmeasured anions in the plasma. Its range of normal values is 3 to 11 milliequivalents per liter, while its elevation is almost always caused by an organic acid metabolic acidosis, like lactic acidosis and diabetic ketoacidosis,